15:35. It's time for everybody to find a seat so that we can start this little quick session and give today's quick speaker, Pontus Hellgren, a big warm applause and allow him to talk about what he do at Discovery.
Thank you so much. Hope you've all had a great coffee break. And today I'm going to be talking about the experiences that I and my team have had in building a global and resilient streaming service API. And just to define what we mean by resilience here is the capacity to recover quickly from difficulties. I took that from Google. But it's basically, if you get knocked down, how quickly can you get up standing again? So, very quickly, who am I? I work with software development my whole career. I've spent almost half of that career at Discovery, where I'm an engineering leader for our backend software development. The main product that I and my teams work with is called Discovery Plus. It's available in lots of different countries around the world. We're up to around 20 million subscribers. If you see the logo here, you can see that we are no longer Discovery, but we just a few weeks ago merged with Warner Media, so we're now Warner Bros. Discovery. So let's talk a little bit about the anatomy of a streaming service. What is it that is actually inside the box? Now, one thing that's a bit interesting or different between a streaming service and lots of other products that you might use is just the breadth of different clients that we have to deal with. Your typical service today might have web, iOS, Android clients, but we are really expected to be on any platform where the consumer is. And that includes lots of different smart TV apps, lots of different set-top boxes, and other bigger and smaller niche types of clients. But the area we'll focus on today is really the dotted box below the clients, where we build a number of different services and service APIs. And this is what handles the backend logic around handling users and their identities, logging in, registering, buying a subscription and paying for it, and of course, serving the content itself, allowing the user to navigate our content library and in the end find something to watch. Then at the bottom you have the parts which are more dealing with the media delivery itself, the actual moving image. And I won't dwell very much into that today, but it's more the backend APIs. And we've been at this for a number of years. We started pretty small, building a brand new platform from scratch. That has grown and grown. It's grown from regional to global. And the position where we are at today is really that we don't have the opportunity to ever be down. It's always prime time somewhere in the world. And we have lots of paying subscribers. They expect the service to always be up and running, and there's very little patience for any disruptions. But incidents will happen. We all know that if we develop software, we will have bugs. So the key thing that we're focusing on is really like, when incidents happen, how do we reduce the blast radius, reduce the impact, and how do we restore service as fast as possible? And even like today, if we have an incident only affecting 0.01%, that sounds like a very small number, it's still thousands of paying subscribers that will suffer from that. So I'm going to be talking about 5 lessons learned, but to frame those lessons learned, I'm going to talk about a specific problem, which is how we render our start page. So this is the start page of Discovery Plus when you go there. It's basically a bunch of videos, shows, channels that you can either click on to play them, or you can drill down further into the library. Now, when we started like 5-6 years ago, this was pretty basic. Our apps would call the REST API, say, hey, give me the data for the start page so I can render that. We had a headless CMS that knew how to assemble these different parts. That service talked to another service that knew about the detailed data for all of our content library. Pretty straightforward. Now, as things have evolved, more features, bells and whistles have been added, more services have been added, we're ending up with a picture that looks more like this. A bunch of different services that are together collaborating to deliver the end result. So more room for error. So what happens when one of these services has an issue and goes down or starts returning errors? What we did have issues with a few years ago was definitely that it knocked down the rest. So the apps would essentially receive a HTTP 500 or similar, and the users would be pretty grumpy and dismayed. So we took a step back and tried to look at, okay, how can we change this so that if one service goes down, it doesn't take down the rest. So this is really what resilience and graceful degradation is about. How can you do as much as possible under the circumstances? So, our first lesson, keep core data very close to you. We will always have services that are reliant on data coming from other services. And to a large extent, we now make our services store local cached versions of that data instead of always being reliant on that the other services are up. Because it's better to serve dirty data than no data. Of course, this is pretty bad advice if you're building a banking app, but if you're building a streaming app, it's fine. It's okay if a video title is a bit old and it hasn't been updated. So really what we're doing is we're optimizing for fast and resilient reads, making sure that those work. We can accept if the writes and the updates are a bit slower and they're eventually consistent. But we also need to pay attention to the fact that there can only be one owner of each logical piece of data. Otherwise, you can get it up into a very messy state. And we basically have two main patterns to handle this. One is what we call our synchronous version, where if one service calls another, it will have a local intermediary cache where it stores all the responses it gets to its requests. So if the other service goes down, you can go on the cached responses instead. The other version is the asynchronous version, where basically all our services publish their primary objects on a message bus. We're using Kafka. And we let other services then subscribe to those entities and store local variations, whatever data they need out of that to do their job. Lesson 2. If things are bad, don't make it worse. Now, if service A is talking to service B is having a problem, it's returning errors, latency is going up, whatever bad is going on. Like what we originally did, which was a mistake, was that, okay, if something doesn't work, let's retry it. Let's try again, and maybe it will come up. Maybe it was just a glitch. The problem with that is that it's like kicking on somebody that's already lying down. You're just going to make it worse. So the way to do this is really to be smarter about it. There are lots of great circuit breaker libraries out there, which will kind of act as an intermediary and make sure that you can do retries, but you need to exponentially back off and do them slower and slower, and maybe even stop doing them for a while. And if you can't get a response at all, the other service is down, try to fail in the favor of the consumer. We had a good example a few years ago where our entitlement service was down. It's the component that actually decides whether can you watch this video or can you not. And we had a big sports event going on. And there we had prepared for this. So we knew that even though we couldn't get that answer, we leaned towards the consumer's favor and decided that, okay, we don't know. We'll treat it as a yes. So that's a good thing to think through ahead of time. Lesson 3, don't assume that your clients are going to be well behaved. Of course, you should have try to have a good relationship with your clients. You should have good API documentation and so on. But really, wish for the best, assume the worst. Rate limiting has helped us a lot just to be able to handle unexpected traffic spikes and other things that we didn't expect. But a good real-world example is something that we've called internally the time bomb. If you look at this graph here, you see that you have these recurring spikes. Those actually happened exactly at midnight. And what we realized in the end that we had was that we had a bunch of clients that had an internal logic or an internal timer, so that at midnight they flushed their internal caches and they repopulated them by calling the server again. Now imagine you have 5 million of these clients spread across the world that are all doing this at the same time. You essentially have a distributed denial of service attack, which can be quite painful. So the other thing to think about here is also, if you can prevent things, at least make sure that you can detect them and act on them. And that goes a lot into logging and making sure that if you have one of these strange situations, how can you actually examine what's going on and understand that, okay, maybe you have this ill-behaving client. Let's throttle or cut that one off, but not cut everyone else off that is behaving. Which leads us into lesson 4. Don't wait for others to tell you that you are failing. This is really about observability and having good logging and metrics. And I would argue that you can almost never have too much logging. I think there are numerous times where we wished that, okay, if we only knew this piece of additional context, we would understand. Instead, you have to do another deployment to add that additional logging, and then you're losing out on solving the issue. A few just small tips and tricks that has helped us is, one is being able to turn on debug logging on an individual user ID. So some user has a problem, we can't recreate it, we can turn on debug logging for just that user. Because you can't turn on debug logging for 20 million users, because then you're just gonna flood your log storage. Good correlation IDs is also really useful, making sure that as requests go from microservice to microservice to microservice, that you're consistent in how you manage the IDs and that you can follow a distributed tracing of what that request, what is going on with that request. And the other thing, which might be obvious, but still, zero error policy. If you don't try to early on make sure that you don't accept errors, you'll end up with so many errors that people think they are normal, and it's very hard to actually single out what are the real issues. But also, even if you don't have errors, absence of errors doesn't always mean that you're okay. We've had incidents where we had no errors, no 500s, everything looked fine, but we weren't getting any payments through. So you also need to look at what is a normal pattern, what are you expecting to see, and make sure that you react on any deviation from that. And also HTTP 400s is a good example. Usually if clients send bad requests, maybe their session is timed out or whatever, it's normal to see a 400. And it's okay to a certain extent. But on the other hand, we've also had a case where we had 2% of all our requests returning HTTP 400s, which was fairly normal. But it turned out that it was actually just one single client that was making 100% total requests. But it originally drowned in the noise before we were able to single that out. And our last lesson, don't rely only on autoscaling. If you're in the cloud and you're using autoscaling, it's a great mechanism. But it can only take you so far. Now, we do lots of live sports events, and there you can go like from almost zero traffic to extreme traffic in literally just a few seconds. And you need to think about this a bit, because autoscaling isn't just gonna spin up 100 new instances in seconds. So first of all, you need to look at how fast do your services start up if you need to spin up new ones. And we're using today a combination of Spring Boot and Vertex. Spring Boot takes up to 15 seconds. Vertex is a bit faster. So you should really know how fast your services can start and tune that. Also, cold pods versus warm pods. You don't want to start a new pod and have it receive end user traffic without having warm caches, because then requests might start taking a lot of time. So you should make sure that you pre-warm your caches before they start engaging with your traffic. And also what we often do is pre-scale before spikes. We had the Olympics games in all of Europe here in both last summer and in February, and literally we applied overcapacity just to be sure before these games started. And we also played around a lot with tuning the CPU thresholds so that we preemptively started up new instances very early on before there was really much indication of lots of traffic coming in. Of course, this is associated with a cost, so that's a business decision if that's okay or not, but at least for the Olympics we figured it was. In Kubernetes we've also learned a couple of things. If you have space in your clusters, you can just ramp up new pods. That's usually pretty quick. But if you reach the capacity and you have to fire up a new EC2 instance, if you're running AWS, that can make the difference between 3 seconds or 60 seconds. Also, we've had to pay attention to IP addresses. Is your subnet running out of IP addresses? Then you can get into a really bad situation. Maybe you need to run bigger nodes just to make sure that you can cram more into one subnet. And last but not least, all managed services aren't trivial to scale at all. We're using a mix of RDS, DynamoDB, other persistent solutions, and RDS can get quite tricky compared to Dynamo and others, which are much easier to manage from a scaling perspective. So, if you just remember one thing from this talk, expect failure, embrace it, and design for it. It's better to have a degraded service than no service at all. That's it for me. Thank you so much for listening.
Thank you, Pontus. The next session will start here in 10 minutes.